that's the stability of the system with respect to oscillatory input. You're left with this triangular white region shown in the middle here, and then you can see a bunch of points illustrated that are given various names, and these are the various classical integration schemes that have been proposed over the last 100 or 200 years. And the one that often you hear in fluids is the Simpson rule or the Adams-Bashforth rule. Probably Adams-Bashforth is the most common. These others are given names according to the sizes of the coefficients. When I did some response of the airplane wing to turbulence, I used, for numerical integration purposes, this 1/2 rule, which I like. And I still think if I was going to pick one again, I'd probably use that same rule. It's the one that's the most accurate of the candidate rules here, and it's well in from the various stability boundaries. So that would be, offhand. I don't want to give people advice because it depends on whether your system's more sensitive to noise or to various perturbations that are static perturbations. But it looks to me like the 1/2 rule would be one that you ought to consider. Well, the average viewer is saying, well, what are these silly rules, 1/2, 1/6, and so on? And here I've given you a table to illustrate these. When you look at the one called Adams-Bashforth that the fluids people are interested in, it has certain specific coefficients involved. The 7 coefficients we were talking about in the Hamming approach are these along this axis, the A0s and through the B2. Simpson's rule is given here. Now you have a chance to look at it, and in the problem session I'll be doing a small example and showing how Simpson's rule is indeed neutrally stable with respect to a static perturbation. And then here are all the other fractional named rules. Well, we've reached a stopping point now in terms of knowing how to integrate a simple system such as a dashpot with a force on it. But really this was just indefinite integration, and we need now to progress to the integration of a true differential equation. To get a differential equation, you need to do something tantamount to adding a spring to the dashpot system. It's said in a more mathematical way here. What you're saying now is that the velocity or the derivative of the function is going to be related to not just a function of time, but a function of where the system is. And this thing called u dot, we have plotted down here. And because you don't know where the system is at the start point in time, you can't calculate the u dot either. And so both of these quantities now become unknown at the current time. You don't know what the force is because you don't know where the system is, and you don't know where the system is because you don't know what the force is. So you can see the tangle that you get into here. And that's precisely what a differential equation is. Maybe you could take a spring damper system and see if you can put it in this form. Now I'm going to suggest another nonlinear differential equation here that would do the same thing. It says that the force is going to vary like u squared plus t squared. So this would be a force that would be increasing in time, but also would increase as the system moved away from its rest position. And this force is tending to pull it further in the same direction as the, in other words, the velocity is increasing as u is increasing. This could be a very unstable system here. I think it's like a negative spring, actually. That would be a good assignment for the viewer to check out. How do you get such a first-order differential equation? And I'm suggesting that this problem here would probably have a negative spring in it, so it'd be a perpetual motion machine if you could get it to work. In any event, we now have to cope with something new, namely that we do not know this quantity, and therefore we can't depend on that quantity in our general formula for finding this quantity over here on displacement. Now, you might think of our indefinite integration as a scheme for finding the function u at a time point where you already know the velocity or the derivative of the function. How can we help that method out by doing something that will give us the estimate of the current velocity, which is unknown? Well, it's called a predictor-corrector method, and we need to develop a prediction of the velocity that's missing now, that used to be known in our integration. And that's called the predictor step. Then we can use our previous information, our previous work on numerical integration as the corrector step. So we already have half the problem solved. Now, what's going to happen is we're going to have to look back farther in time in order to get enough information for a 7-parameter formula. Why? Because we're missing this current velocity. This is more error-prone to do this because you have more history behind you. We are going to call it the predictor step. And then that will provide the velocity that we're interested in that's been unknown till now, and then we put that into the corrector step. We're going to use the same number of parameters as we did before, namely the 7, and we're going to use the same in the predictor and the corrector formulas. Also, when the push comes to shove, we're going to try to keep those formulas as close as they can. I'm sure there are viewers out there who are watching this and saying, well, what's this guy doing to me now? I thought I understood. Here we were doing nicely integrating and tripping gaily down the primrose path, and all of a sudden he shows me that what we were doing doesn't really apply directly to differential equations. And that's right. We need to develop this predictor approach, but I didn't want to complicate things too quick for you. Now, there would be two ways to do a predictor step. One would be to go back further in time and pick up a displacement, and the other would be to go back farther in time and pick up a velocity. So there are two classes of predictor formulas. Here's a Milne-type predictor shown at the beginning here, and that has gone back and picked up a displacement from the time step n minus 3. The Adams-Bashforth type predictors has gone back and picked up a velocity at time step n minus 3. And of these two, it will turn out that the Adams-Bashforth is the more popular predictor. And one reason is then that the A coefficients here can be similar as they were in the corrector step, or what we had done previously. Let me repeat the corrector formula so that you'll have those different choices in front of you. Here's the displacement at time n plus 1, and rather than calling it u, we're going to call it c. And I think if you noticed on the previous formula, you would notice that I was calling the displacement p for predictor. Really, those are both displacement estimates for this quantity here. And what we're talking about is trying to predict this. Now, the two cases are whether or not you know this blue star over here, which is true in the corrector stage. You pretend that you know that when that shows up right here. But on the predictor phase, that point is missing, and then you have to pick up either this round blue circle here or this one here, depending whether you're using the Milne or the Adams-Bashforth approach. And as we've mentioned, it's more common, at least in fluids, to use this point here on the velocity as the point that you go back and pick up. Let's discuss the criteria for choosing a method. Goals that we should have would involve low truncation error, large margin of stability, and protection against round-off error. Round-off means the same thing as noise, because in a computer calculation you get the twittering of the last significant figure due to round-off, and that can introduce an oscillatory effect into a computation. So this is basically what we call noise. Now, in achieving these goals for the integration of first-order differential equations, it's become common to use the Adams-Bashforth approach, because when you use it, you have the same coefficients on the displacement terms in the sampling. And that means when you compare the predicted value and the corrected value for displacement, all those terms cancel out, and you're only left with these terms below that are all on the velocity sample terms. So pretty much Adams-Bashforth is the method you hear. When you go to fluid mechanics seminars, you hear a lot about that. The class of predictors that use an additional velocity term are called Adams-Bashforth type of predictor. I'm going to give you a table here showing a number of those predictors, including one that is specifically called the Adams-Bashforth method. These coefficients are rather intricate, as you can see, and had to be developed by the same stability and accuracy arguments that we used on the corrector. In our problem session, we'll start by looking at Simpson's rule for integration. And here we're going to look at the indefinite integration, in other words, the corrector form, in the presence of a perturbation. So we're going to look at the stability of Simpson's rule. And then, after looking at stability with respect to just a static perturbation, let's look at it with respect to some noise that moves with oscillation plus minus E, and see how that jiggles the system. It's not clear how we're going to put this into the system right now. We can do that through the displacement field, but I'll show you how to do that in a second. So I've written out the equations that result from the need for accuracy, and our general integration formula here becomes Simpson's rule when you put in the remaining values for A1 and A2. Now for our stability study, we're going to do a perturbation. We'll hold the velocity 0. I won't plot that this time, and we'll show that the little chart that I like to use has an epsilon here at time step 0. And then when we carry out the succeeding time steps, we find that we get an oscillatory answer as shown over here. So the small static perturbation here has led to this dynamic oscillation. People might call this neutrally stable, and this could be acceptable in quite a few situations since it doesn't amplify. And maybe in some other situations it wouldn't be acceptable. In the second part of this problem, I wanted to look at noise, and it's a little bit argumentative how to introduce noise into this system. One way to do it would be to shake the system at that noise and then stop and see what happens. So that's what I've done. So I've continued the process for several steps here and then found what happened at the following step. And when you do that, you find that the oscillation continues. So it's not quite a good study on noise, but I think it shows that you have the same instability there that we did on the static perturbation. Let's do a practical indefinite integration with a specific dashpot and a specific load applied to it. Suppose this system's at rest at time 0, and then we use the 1/2 rule for integrating to find where it is at time increments of 1,000th of a second and 2,000th of a second later. The load is 100 newtons applied at time 0, so I use this Heaviside step function here to illustrate that the time at time 0 the load starts, and before that the load's not there. And then the damping coefficient is 10 newton seconds per millimeter. The differential equation would be this. Our initial condition would be like this. We've said that this actually equals 0 at time 0, so we'll set that to be 0. And then the integral form of that is shown here, where we would again set this to be 0. We can see just from elementary physics that the velocity is going to be 10 millimeters per second, and it really should travel 1/100th of a millimeter in each time increment. Then let's just see if we get that out of our integration. Let's use the coefficients from our table to go into Hamming's general formula and get the specific integrating formula. Here's the general formula, and then here's the specific one for the half rule, putting in those constants. Then I set up the table as we've done before with 1,000th second increments, showing that the system is at rest for negative times and up to time 0. Then we find the displacement building up here as 1/100th of a millimeter and 2/100ths and 5/100ths. Now, this is more than the classical result, so we can see that we're overestimating the displacement in this situation. Although I filled in those answers in the previous slide, here I have the actual calculations that were done, and these show how indeed the displacement after 1,000th of a second is this 0.014 millimeters, and then after 2,000ths of a second, and then I just state the displacement at the third time step. So this method is overestimating displacement by a sizable percentage. What happens though as time goes on is that generally these methods home in, and if you're getting bad answers, and I would consider this very borderline good, I mean it's sort of bad, then you have to take smaller time steps. So the viewer might look at this problem and then try this calculation over again with time steps that are much smaller, and then observe how the method converges to a better, more accurate answer. I was interested in the stability of the Adams-Bashforth-corrector formula, and since it lay on the boundary of the stable region, so let's do a little check on that and check it for a static perturbation. Let's suppose we want to integrate this formula in the presence of a disturbance. That's what we've been doing before. We'll give a little epsilon disturbance. The Adams-Bashforth formula gives you certain coefficients, and here is the integrating formula. This is fairly predictable that the current displacement is the same as the past displacement under this condition. So I think this, now that's just under this condition. This isn't the general formula because we've dropped out all the velocity terms. So it looks as if it's going to be somewhat stable. So the Adams-Bashforth corrector formula isn't very exotic when you do it with the system at rest and no velocity and no force applied, and then bump it a little bit, and it just sits there, as we can easily see. When we calculate our table here, we find that the displacement at the time plus 1 here is the same as the past one, and same as the past one, and same as the past one. So this is just a neutrally stable method in that sense, that you keep the perturbation displacement, but it doesn't grow, nor does it die out in time. And this is probably okay. And in our integration case, it's like disturbing the dashpot from its equilibrium position, and then it just sits there. So actually, physically, this is rather understandable for our mechanical model of a first-order system. Well, that finishes our lecture on numerical integration of first-order equations, and it's meant to really be inspiration and kind of enlightening about what stability means, and then prepare us for more serious work on second-order differential equations coming up next.